we were discussing about doublet and we will continue with that. So, if you recall the previous lecture, the complex potential for the doublet can be written in this particular form. Now, what kind of flow does it indicate? Remember, let us keep this at one side of the board, so that we can relate it with what exercise we are doing today. So, the complex potential is defined as phi plus I psi and its derivative is u minus I v, and in r theta coordinate V r minus I v theta into e to the power minus I theta. I guess we have derived this, right. Okay. So, now this is phi plus I psi. So, actually the problem in terms of complex analysis is separate this into real and imaginary parts. Real part will be velocity potential and imaginary part will be stream function. So, we write so to make the denominator real, we multiply both numerator and denominator by x minus I y. So, this becomes m into x minus I y, this is x square minus I square y square, and I square is minus 1. So, this is x square plus y square. So, if this is equal to phi plus I psi, then what is phi? And psi is minus m y by x square plus y square. So, let us try to draw phi equal to constant lines and psi equal to constant lines. So, phi equal to constant. So, you can write x square plus y square minus mx by phi equal to 0, right. So, you have x square minus 2 into m by 2 phi x plus m by 2 phi square plus y square is equal to m by 2 phi square, right. So, this is x minus m by 2 phi square plus y square is equal to m by 2 phi square. So, this is as good as x minus a whole square plus y square equal to r square. So, this is equation of a circle with center at m by 2 phi comma 0 and radius m by 2 phi. So, let us try to make a sketch of this. So, x equal to m by 2 phi. Now, this phi can be positive, negative, whatever. So, let us take one particular say arbitrary point here which is m by 2 phi and y equal to 0 and the radius itself is m by 2 phi. So, in this way if you take say this point as the center, the radius will be this much because center x coordinate and the radial coordinate they are the same. So, that will be a bigger circle like this. So, m by 2 phi, this is also m by 2 phi, I mean this is because hand sketch, this may not look exactly the same, but this is m by 2 phi, this is m by 2 phi and radius is the center is m by 2 phi comma 0. So, in this way, so let us say this is some value 1, this is 1.5 like that. What happens if it is say minus 1, say in the negative side of the x axis. So, if this is minus 1, so like this the radius is still the same. So, you can see basically a mirror image of the same thing with respect to the y axis. Like this. So, these are all phi equal to constant lines, these white colored lines. I will draw the psi equal to constant lines with a different color, so that it is easy for you to follow. Now, let us try to draw the psi equal to constant lines. So, psi equal to constant, so let me write somewhere here, maybe I will utilize this same space. So, x square plus y square plus my by psi equal to 0. So, x square plus y square plus 2m by 2 psi y plus m by 2 psi so x square plus y plus m by 2 psi square is equal to m by 2 psi square. So, this is also equation of a circle with center at x equal to 0 and y equal to minus m by 2 psi. So, that is on the y axis and radius is m by 2 psi. So, it will be something like this. So, if this be the center, this much will be the radius. Similarly, you can draw something for a higher radius. So, these pink colored lines are psi equal to constant. So, you can see very easily without calculating the psi equal to constant or phi equal to constant line equations, if we know one of the equations, we can clearly draw the other from the consideration that they must be orthogonal to each other. So, these circles, wherever they intersect, if you draw a common tangent, they must be orthogonal. So, so far we have discussed about uniform flow, Rankine oval, and combination of source and sink, source sink individually and combination of source and sink, which we call as doublet. Now, I will tell you something which is more interesting. This is something up to this we have done exercise which is primarily of academic nature, but you may argue that this kind of source sink located at a certain distance apart, what practical flow does it represent? If it does not represent a practical flow, it is not of that interest. Let us now imagine that instead of this kind of flow, you want to model a practical flow over a body of the shape of a cylinder. So, cylinder is of course not the most general shape, but cylinder is ideal or an idealized geometrical shape, and streamlines and equipotential lines for flow past a cylinder can give a qualitative understanding of flow of a fluid over bodies of much more complicated shapes. So, one of the elementary things for studying aerodynamics is to first understand what is the flow past a circular cylinder. So, we will start with our objective of generating the shape of a body through the superposition of complex potentials which represent the flow past a circular cylinder. So, I will show you that this nice combination uniform flow plus doublet can achieve this feat. So, how do we show that a uniform flow plus a doublet can be used to model the potential flow past a circular cylinder? So, to do that, we will write the complex potential, and this is the great advantage of the linearity of the problem, that if F equal to F1 is a complex potential for uniform flow and F equal to F2 is a complex potential for doublet, then for the combination the complex potential is F1 plus F2, because F is what, phi plus I psi, and phi and psi both satisfy the Laplace equation, which is a linear second order partial differential equation for this 2-dimensional flow, 2-dimensional irrotational flow. So, F is equal to what? Uniform flow means uniform flow could be along any direction. Let us say, let us augment this by saying uniform flow along x, that makes it u infinity z, and doublet is m by z, where m is called the strength of the doublet. So, this parameter you have to choose, actually we are keeping it open at this stage. So, if this be f, then df dz is what? Df dz is u infinity minus m by z square. right. So, this is I have erased that part, but it is nothing but V r minus I V theta into e to the power minus I theta. So, if you want to bring e to the power minus I theta as common, then you can write this as u infinity e to the power I theta, because we will then multiply with e to the power minus I theta to make it u infinity, minus m z is r e to the power I theta. So, this is r square, e to the power minus I theta is already there, and so e to the power minus I theta and then e to the power minus I theta. Okay. Now, we will write e to the power I theta as cos theta plus I sin theta, because we have to somehow separate the V r and the V theta part. So, u infinity cos theta plus I sin theta minus m by r square okay. So, now this is u infinity minus m by r square cos theta plus u infinity plus m by r square I sin theta. So, this if you compare this with V r minus I V theta, this expression, then this is as good as V r and this is as good as V theta. This, by this I mean includes sin theta and cos theta also, right. So, now imagine the flow past a circular cylinder. If you imagine flow past a circular cylinder, what is the basic boundary condition that this flow must satisfy? On the surface of the cylinder is defined by a constant radius. On the surface of the cylinder you must have no penetration boundary condition. That means at small r equal to capital R, which is the radius of the cylinder, you must have V r equal to 0. This is no penetration. No penetration boundary condition is very, very important, because it does not depend on whether it is potential flow or not. No penetration is a kind of kinematic boundary condition at the surface. So, kinematically there cannot be any penetration across the surface until and unless there is a hole. That is what is being represented by the no penetration boundary condition. So, for the no penetration boundary condition, you must have u infinity minus m by r square, that must be 0. So, at small r equal to capital R, you must have V r equal to 0. So, you can set the strength of the doublet as u infinity r square. Okay. So, this is the first thing. Then what is V theta? At small r equal to capital R, at small r equal to capital R, V theta is u infinity plus m by r square sin theta. M is u infinity r square, right. So, 2 u infinity sin theta with a minus sign, because actually it is minus V theta. So, minus V theta is this one. Okay. So, interestingly, see, V theta is what? V theta is the tangential velocity on the surface of a, say, cylinder. So, by setting V theta equal to this at the surface of the cylinder, we are allowing slip. So, we can clearly understand that where viscous effects are not present, slip must be allowed. Otherwise, you cannot satisfy the requirements of continuity and momentum conservation on the surface. So, this is the Vr and V theta, we will come to that, but before that it may be interesting to draw the streamlines. So, to draw the streamlines, f is u infinity, z is x plus iy plus, or you can even write in terms of r and theta. U infinity into r e to the power I theta plus m by r e to the power minus I theta. So, u infinity r cos theta plus I sin theta plus m by r into cos theta minus I sin theta. Okay. So, f will be u infinity r plus m by r cos theta plus u infinity r minus m by r sin theta into I. Now, what happens at, look at the expressions for velocity also. So, what happens at theta equal to 0 and theta equal to pi? Vr is 0 for all locations on the cylinder, that is how it is designed. V theta will be 0 when theta is 0 and theta is pi. So, at theta equal to 0 and theta equal to pi, you have both Vr and V theta 0, that means the resultant velocity is 0. So, these are called as stagnation points. Now, at small r equal to capital, so m is u infinity into r square, right, and here also m is u infinity into r square. So, first of all, when small r is equal to capital R, so this is phi, this is psi, right. So, when small r equal to capital R, so let us draw the cylinder. We are talking about the cylinder for so long, but we have not drawn the cylinder. Let us draw the cylinder. Let us say the cylinder is located like this, and u infinity, the flow is coming from this side. So, now so this is psi, right, not phi. When small r is equal to capital R, psi is equal to 0. So, this is itself a streamline with psi equal to 0. When small r is greater than capital R and when small r is less than capital R, you will get two different types of like one is, in one case this term will be greater than this term, in one case this term will be greater than this term. So, small r less than capital R and small r greater than capital R will be two different cases, out of which case will be interesting? The case with small r greater than capital R is interesting, because we are interested to model flow external to a circular cylinder. What happens inside happens, but that is not of our interest to us. So, flow inside the circular cylinder is like artificial, it is not of a matter of interest, because in reality, you know, it is a blocked cylinder. This will of course give Vr, V theta etc. inside the circular cylinder, or phi, psi and all this, but these are of not great importance. So, you have u infinity r minus u infinity r square by r, this into sin theta. So, you can clearly see that psi will be 0 at theta equal to 0 and theta equal to pi. So, at theta equal to 0 and theta equal to pi, the streamlines should be emerging like this. They should be representing psi equal to 0. No matter whatever is the r, if theta equal to 0, this will be 0, right. But if theta is not equal to 0, you can make a plot of this and you will see that the streamlines will look something like this. Very, very symmetric. This symmetry can be broken if viscous effects are brought in, and then this symmetry breaking phenomenon due to viscous effects can give rise to a drag force on the cylinder. However, without considering the viscous effect, we can get significant insights on the pressure distribution on the cylinder, at least up to the region over which this kind of streamline pattern is maintained. If there is viscous effect, then there can be a phenomenon called as flow separation at the back face of the cylinder, which is also called as wake. So, in that scenario, this nature of the streamlines, this may be disturbed, but in the front side this nature of the streamlines will be maintained to a large extent, at least say up to theta equal to 90 degree, and then there is likely to be a remarkable agreement between the pressure distribution that you get out of the potential flow solution with a pressure distribution in a more realistic solution, which is a viscous flow solution, to an extent up to which this kind of streamline pattern is maintained. So, therefore, getting an expression for the pressure distribution around the body is a matter of great importance for us, and we will take that up in the next lecture. Thank you.